the control channels of the algorithm as explained by steepest descent earlier. So there's a comprehensive list of blocks. You've seen them graphically in the little snapshots I showed, and at the end we'll give you a document with a detailed explanation of all the components in here. So the second component is performance. Productivity, now I have my design entered like out of the textbook, but not starting with C++ from scratch. I have taken models and connected them. Now I want to go through the simulation. So simulation speed is very important, and one of the things we have done that's actually a patented and I think trademark term, so I violate my own product management rules by not putting a TM on here. So it's a stream-driven simulation where in the data flow domain, where a lot of it is taking one block which fires a certain amount of elements, connecting to another block which can execute and consume a certain amount of data in a certain amount of time. We do pre-scheduling in advance of the actual simulation, so there's very little discrete event simulation going on by having as much pre-scheduled as possible. We have especially a need to optimize in this domain the fixed point simulation, speeding up the data types you get from System C, it's one of the modeling infrastructures, to get this almost to floating point speeds. And you also need to be able, given that you have to run thousands of simulations for generating those bit error curves, you need to be able to take simulations and distribute them across different cores and across different computers in a framework. So that's something we have been working on. Here's one requirement here. As I pointed out, you have to get one performance point in the signal-to-noise ratio bit error rate curve. You need to basically simulate a large number of data samples to just get one performance point. So you need to be able to simulate a large number of input data, and we have in this particular case the demand for getting compiled C++ simulations so that things get as fast as possible to get you a curve like that overnight once you have changed the channel characteristics, the parameters in your algorithm. When fastest simulation on a per instant basis is not enough, just as I just mentioned, you will need to refer to parallel iterations where you now spread these items in parallel over a number of CPU cores. So we have already announced, for example, cooperations with Microsoft, where we run on the the parallel servers for the Microsoft OS to enable the parallel execution here of multiple simulations to get to bit error, to fast results for bit error rates. So from a simulation speed, you always find this, have a trade-off here between being able to simulate things as fast as possible, which leads to native data types, but then you want to be able to model very efficiently what's going on in your algorithm, especially taking into account the architecture you're mapping this towards. So that calls for fixed point libraries, and the designer's wish is really, the objective is to get this into a domain where you get the fastest speed with the best modeling efficiency. So that's the designer's dream, the designer's wish, and no surprise, as I will tell you at the end, that our tools help designers to get closer in this domain here. The third component is the notion of flow integration. Once I have refined, and this is going back to Chris's slide where he was showing the methodology and the refinement flow from the purely floating point algorithmic model all the way down to RTL. This is essentially the integration I'm referring to here, where the tools need to be able from a high level to connect to verification and even to software development by allowing you to reuse the algorithm work you do at the high level, taking steepest descent libraries, for example. Use that as a golden reference for your hardware development, then take it over use it as a reference for the embedded software developer, so that the embedded software developer can start prior to the actual chip being available, which will overall greatly de-risk your flow, make your risk much smaller, because you're building up top-down from the development of the algorithm. So we have a couple of export capabilities which users are asking for integrating. They need to be able to export to System C, which is a simulation infrastructure for algorithms and implementations. You need to be able to put the utilities around that, the make files, the test benches. We need to be able to export into HDL simulation, where really you have a knowledge transfer, taking the algorithm user who has all steepest descent knowledge covered and captured in their libraries, giving that to an RTL designer whose core competence is to develop the chip downstream. He doesn't want to know about the actual algorithm components in the very front end because he's not an algorithm expert. He still needs to do the in and output data and use those for verification. Another requirement users give us is to import HDL into the high-level interface, where we basically are able to synchronize simulation engines and take the HDL back into the system-level model. That is a requirement for verification. And then in an ideal world, but we are not quite there yet, users are asking for automated RTL code generation, just like Tensilica, as Chris pointed out, is giving you as one of the deliverables at the end the RTL of the processor together with all the software tools you need specifically for this processor. People would like to have for the hardware components, and Chris was pointing to that with the TIE extensions, the Tensilica instruction extensions, and the hardware components being able to generate out of this. People would like to do this for general hardware accelerator blocks as well. And we have requests to basically either do high-level synthesis or be able to generate at least the HDL co-simulation for verification and do some level of translation here. So here you see one of those components where you have a C++ interface which we automatically generate around the algorithmic model to generate a System C wrapper so that you can import that into your simulation. And as I mentioned earlier, going back again to the discussion we had earlier, this is a real knowledge transfer, right? So there's no knowledge of the higher level model. It's really necessary once you go to implementation. At the end of the day, the last requirement here, people really would like to take this and then map some of it in the hardware and run hardware in the loop simulation. So that's another requirement for flow integration. And here's an example of how high-level models are used in virtual platforms. I can take for a picture application, take the infrastructure, the picture generation, the rendering, and the analysis, and take this as a environment model and a part of my chip, import that into a virtual platform, and then simulate really in my SoC, which goes into this camera, with the software debugger attached to it long before the actual chip is available. So I can go from a algorithm model, and again, that's how we all tie together. The algorithm model would come from steepest descent, would be the modem in here. I would have a processor for which I would go to Chris, and then we have the tools to tie this all together to basically allow you efficient development of the software early on. So the 5 requirements and the needs users express are model-based design, that gives you the productivity, simulation performance for highest execution speed here, debug, the models for the model-based design, and then integration with the flows downstream. And no surprise, that's the type of requirements and needs which we are gearing our tools towards. So you have libraries here which come with System Studio. For LTE specific libraries, you can we are working together with Steepest Descent, and then we have the model-based design environment which allows you to put just the algorithm together. So this is now a subsystem in your overall chip, which you will put into your 4G cell phone at the end of the day, or the 4G device. Now I want to take that particular portion, which is just one building block, put it together with other processors, the application processing world. I want to be able at the end to test how my app store is working on it. And this is the area of hardware-software optimization. And just to give you a little bit understanding of the pain which the chip developer feels. So we had a little poll of the audience. You mentioned you're in system engineering. Is there any chip development house in the room? Anybody doing chips? You're doing systems or software? Software? And for you also software? So this is the pain which the chip developer feels, who is supplying the chip or the device for you to develop the software on. So this is real data measured in a project over 2 or 3.5 years in a wireless design, where you have an initial design which always took 9 months to get to the first chip. So I have my post-silicon validation on the prototype. Well, they found some issues. I have my first respin, so I had to respin the design, do more post-silicon validation, have a third design phase, and then finally here they get into volume production. So somewhere after 2.5 years, they actually just broke even with their development costs versus the actual revenue they got with it. So the idea here is now to have a prototype for software development available very early in the design cycle, as opposed to very late after 9 or 12 months here. So one of the things our industry has started developing is this notion of virtualization for the embedded hardware. So instead of dealing with this nightmare prototype in the lab, we are enabling users to build a fully functional software model. So it's actually something I can show you on my machine. I can show you an OMAP 2420 or an OMAP 30 series running as a virtual model on my PC, executing the same code I would beam later on into my actual hardware once it becomes available. Only big difference is, while this is still running at real time, the biggest difference is, given that it's software and a simulation, I have full insight and full control. So I can stop the processor, I can interact with Chris's delivery, the Tensilica core, the data plane processor, the data plane engine, and stop it at any given point in time and see how my software, where my software is at it, so I can look for even things like multi-core issues like races and deadlocks. So the other item, despite the fact that it's much easier to control and much easier to look into, is that it's available much, much earlier. So I have this device basically available sometimes 9 to 12 months before the actual chip is available. So this really helps you with parallelizing the design flow, meaning I can get my hardware and software closer together, get to market early, and then obviously the objective here is to get the profit higher, because I can, being early to market, I can charge more. Here's a real example of a platform, actually a wireless platform, which is a couple of years old, but it's showing you the basic use model. You start with your specification of your chip. We are able to give you a virtualized version of this chip very early, and you have the first driver developers, firmware developers starting to use it, ramping up to about 40 to 50 users in the software domain, really now using virtual platform before the actual chip is available. And then when the chip is becoming available, obviously a lot of those users will start using real dev kits, real development boards. So the virtual platforms in general, and this is not Synopsys specific, there are other tools out there, like Chris mentioned, companies like Cover, Vast, Rigitech are in this domain as well. You take in the most general form libraries, so we have libraries for architecture components, Steepest Ascent has algorithm components, you would specify based on standards, new components, and import your system C, and we allow you to create a platform. So there's a canvas on which you drag and drop those architecture components, just like the model-based tools I introduced earlier a little bit are canvases for just the functional component of the algorithm. This is bringing in now the Tensilica core. So as this is the same screen, the same environment of which Chris showed screenshots earlier. So I put together my platform, I execute the software on it, I debug it, and then I deliver it to the software developer, who now gets a runtime executable. He can't make any changes anymore, but he can attach the third-party software debuggers to basically debug the software together with in the hardware context. So there are a couple of use models here, and in the interest of time, I'll go only very briefly through them. The first use model is software development, where you need high-performance simulation of a complete system. You need standards. So our industry, the EDA industry, has developed standards by which different vendors can interoperate. The TLM2 standard is very important here. And it's we are integrating with the embedded software toolchain so that the software developer doesn't need to change the environment they are working in already. So you have an IDE from which you deliver a runtime environment which looks very familiar to the software developer. We provide libraries of processors, connectivity models, even pre-assembled platforms. The key portion here is that they need to be tool independent. So our libraries work even in competitive simulators or in the open system C infrastructure. They're following the TLM2 standards. And here's an example. All the OMAP platforms until 3430 have been, and that's publicly announced, have been developed, have had these models, so the software developers could ramp up software development much earlier than normal, and they were available 12 months before hardware. So TI at the time developed 85 to 90% of their software pre-silicon. There's a nice quote here. You find all that in the handout for those of you just joining. There are handouts in the back of the room. The second use model pertains to how to integrate with the rest of the flow once you're done with the algorithm and the integration. So with connecting to RTL, to the implementation world, into the system to silicon flows, you can link into hardware, you can link into implementation from your high-level model. So you take a high-level platform, and here you now take a implementation subsystem and connect that to your high-level model for verification purposes. So you run your implementation together with a high-level virtual model of your design. So this is an example here. I have a platform with software attached to it, and I go all the way down to the Verilog, which is the language in which the hardware is developed, with things like assertions like the hardware equivalent of breakpoints, and I can co-debug all this together, even connecting the high-level world with the actual prototype, so I can take the best of both worlds here and offload my software from here to the workstation, use it as verification reference, or connect to outside interfaces like the air interface and hardware, and still keep my software simulation in that same context. So with these hybrid offerings, we get even further schedule improvements by breaking this traditional serial flow of software following hardware by bringing software in to a much earlier point in the design cycle. Last item, and Chris was referring to that a little bit earlier by pointing to performance profiling and like things like bus bandwidths. Once they have generated a new version of the Tensilica core in what Chris called the language of the LTE processing options there, once you have those generated, you want to be able to do performance analysis, and you need different abstraction levels for this. So you can use more accuracy, in which case the models get slower, but you have more data available and more fidelity in your models. And you can basically choose different use models here, where for architecture exploration you typically take one in between. You take a model to which you annotate timing to allow architecture exploration and more real-time software development. So this analysis, going through the details here a little bit, you take your virtual platform, log data into files, and then you have display options like looking into transactions, the actual waveforms, the software execution on top of it, cache statistics, and then, as Chris already pointed out, things like bus transfer and overhead statistics and bus burst statistics, which all help you now to feed back. There was a spider web which Chris showed, where you had the algorithm, the ISS, and then you generate architecture specific things and you go back and forth in the spider web. This is one data source for making decisions in the spider web. Do I need to go another optimization because my bus bandwidth is not where I would like it to be? So this is one of those feedback loops. So again, given that most of the items were general, and I even mentioned our valued competition in this synopsis in this domain, especially for wireless, and now with LTE, that's just the next step, has been a leader in wireless with libraries, the tools for integrating those things together. So here you see an OMAP in a virtualized fashion, and we have expert services which help companies like TI, Marvell, and Freescale to develop their wireless platforms like the OMAP application processor, for example. So just to bring it all together at the end, we were, as a tool provider, really the glue to keep these things together. So the reason for the session today was to give you a little glimpse of the ecosystem, and as an example, I used virtual platforms here, where the idea is to break through this traditional cycle of serial development of software after hardware to get the software development early. I need models for multiple vendors. So Chris may sell me one model, but I have a lot of I have a lot of software still running on another processor. So I have models coming from multiple vendors. I have different options of simulators. I have different options for debug. I need specific driver software. I need algorithms from various sources, which makes it a real nightmare for somebody to put all these items together. So here you see a glimpse of the ecosystem, where today we only gave you really feedback, or we only showed you a couple of corner items here in the model scenario, where we interface with steepest descent on the algorithm side, we interface with Tensilica on the processor model and the subsystem side. The ecosystem is much bigger. We have, for example, libraries which work in competitive simulators like Cover and VAST. We work with automated implementation vendors who take hardware description languages and implement them in hardware automatically from the high-level models we give them. We have companies dealing with verification interfaces, and then you have the whole embedded software side, where you have driver development companies developing middleware and driver stacks for certain components, and you have debuggers in here hooking up to the models, just like Chris pointed out. So this is quite a complex ecosystem which needs to be in place to interact seamlessly with each other, so that the chip providers giving you the chip, and then at the end the systems on which you develop the software, can actually do their job. And today we basically just gave you a glimpse on Synopsys with architecture models, Tensilica, and functional models with steepest descent. So just to summarize, so steepest descent and Synopsys, you take their libraries and take them into our tools to give you the model-based design entry for algorithm optimization. Chris had pointed already to this slide, where you have a Tensilica core So this is the custom processor which Chris had just optimized to meet specific computational requirements dictated by the LTE standard and the algorithms. So that's now getting together, potentially executing some parts of the algorithms coming from steepest descent and software, where others are mapped into hardware. And so we are the glue keeping it all together with the models here. So that's really bringing us to an end, catching up almost in time, only 10 minutes late. So for those challenges of signal processing algorithms, we have System Studio as one of the offerings. For the challenge of getting you to software development early, we have Innovator, and on top of it, we provide services around that, which really brings now the chip developer much faster to the end results. With that, open it up for questions.
So why don't all three of you get up there? All right.
Okay, cool.
And with our few minutes remaining, I've got a simple question to start you guys off. Okay? Yesterday I saw all the app guys. They were all in the room over there on the right. And they're a crazy bunch. From their viewpoint, they don't want to hear about nothing. From their viewpoint, it's all IP, and they intend to write in XML. They never want to know anything about what's happening underneath. Okay? So how do their requirements, which are basically non-existent other than give me a lot of bandwidth, translate into your guys' work? When do you hear from people, well, here's what I know they need that they haven't asked for? Is that happening, or is it kind of a real disconnect?
I don't think it's a real disconnect. I think the transmission between the application guys and what we do tends to be a handset or hardware platform system supplier and a semiconductor supplier who are saying, yeah, we are going to deliver to the application guy that illusion of lots of bandwidth, lots of mobility, all IP. But under the covers, there's a hell of a lot of work to do to implement that. And I think the guys making the handsets and the guys making the silicon, which really are all of the guts of the handset, have a huge task in front of them. And we're here really as facilitators of that category of people to make it easier to do that thing. But there's nothing unreasonable that the application guys are asking for. As a consumer of a wireless device, I want it to be, all IP all the time. I want it to be small. I want the battery to last for a lot longer than it lasts today. And therefore, those fundamental things, cheap, low power, high performance, meaning lots of bits. And by the way, I also want it to have some flexibility. I don't want the handset guy saying, oh, for that feature? Let me sell you a new piece of equipment.
Exactly. And on top of it, it's a typical loop of guys beating each other up, typically on landlines. So Chris's processor has been integrated with steepest descent algorithms running on it, with a platform we provide, a virtual platform, has been given to software developers. So now it's in a chip by, let's say, semiconductor XYZ. They chip that virtual platform all the way to Northern Europe, and then some grim-looking guys bring up their early software, bring up their applications on top of this virtual model, figure out, oh, the bandwidth doesn't work, and now they come back, they beat up semiconductor company XYZ, they got an angry phone call in Finnish, and they go back, oh, Chris had given me the spaceband engine. Well, it wasn't quite in the upper left side of Chris's diagram of the performance power graph where we should have bought it. So they come back to Chris, want a better processor, and the whole cycle starts again. So we see the application requirements coming back immediately into the tools, into the IP, into the algorithms to tweak the application tweak the implementation for the next time around. The challenge is there's a fair amount of phone calls and level of remoteness in between. So we are trying to predict what the application developers are doing. That's why I'm here, So I want to hear what's their biggest requirement so that I can make sure our tools can simulate it, and that I can make my calls which IP providers, both functional and architectural, I best work with because they have the best solution in that domain. So it's a back and forth. And one interaction point which is very famous is look at the iPhone and the software development kit, which sold like in the first 4 days like 100,000 times for people developing applications. That's where on the tool side the intersection point happens, because we have to model all those components, the functional algorithm, the architecture underneath in those SDKs, so that at the end of the day the application developer sees what they're developing on.
Frank, you're quiet, so let me ask you something about the library side of the equation.
There you go.
So when I was watching you talk about the libraries, one of the things that really hit me real quickly was I was saying to myself, well, it looks to me like I can have a natural symmetry on the transmit side and on the receive side, and I can screw myself up by trying to tweak one over the other. And I said, well, wait a minute, that's not the way LTE works. LTE expects a much bigger down pipe than an up pipe. So I'm asking myself the question, is the way that the libraries work designed to deal with the throughputs expectations from the down versus the transmit?
Absolutely. That's taken into consideration in the specifications of the standard. And what we do when we implement those is there's some leverage for doing independent signal processing, but the standard says govern the data rates. So you need to maintain your design so that they adhere to those data rates in both the transmit and the receive end of it.
Yeah, and just to follow up on that, it certainly is the case that the data rates are higher in the downlink direction, and generally receivers are a lot harder than transmitters. Receivers are harder, particularly because you're correcting errors or you're extracting signals rather than just encoding them. So that means that actually in the whole wireless system, the whole thing which is hardest is probably the handset receiver, because it's got to receive all that bandwidth and it's got to do the deciphering of what that is, and that's multiplied by MIMO effect. That being said, I think from a modeling standpoint, the most important thing is to have great tools. That is, you want to have the components, you want to be able to look at it abstractly, initially without caring about exactly how many cycles per second, max per second it requires, because you got to get it right first. And then you start confronting the question of, oh my God, I've got to go do, 50 billion operations per second to do what this algorithm implies. And maybe you have to at some point go back to the algorithms and come up with some clever algorithms to reduce the compute. But you want to have some separation, some layering there, so you can deal first with the question of what's the protocol and how does it work, and then with the question of how does it actually map into hardware that will run in 300 milliwatts so that somebody will buy my handset.
Guys, let me give you guys a round of applause again. Thank you for coming. All right, let's get you set up over there, and we'll move things forward.